We're now going to talk about a rounding rule that we're going to use when we calculate the mean and standard deviation. And this is actually pretty important because you need to get the numbers in correctly into Connect Math in order to get the right answer. And so it's going to want you to follow this rounding rule here. So it's basically you're going to round the mean and standard deviation to one more decimal place than the observations in the data set. Okay, that's the rounding rule. So let me just give you a couple examples to show you what this means. So the first example here, we got some, let's say some scores here, 76, 89, 71, 64, 84, 63, and 61. And we're going to calculate the mean. I'll use that X bar symbol here. And if we add all these up here, I'm going to go ahead and do it. 76 plus 89 plus 71 plus 64 plus 84 plus 63 plus 61. And they all add up to 508. Okay, and we're going to divide by 1, 2, 3, 4, 5, 6, 7. Divide by 7. And I get a repeating decimal, something with a bunch of decimal places. So it's like 72.5714285771428. It probably repeats itself. Okay, so when this happens, we're going to need to round the mean. And the rule that we're going to use is we're going to round to one more decimal place than the observations in the data set. So all these scores here are rounded to the ones place. So I'm going to round this to the tenths place. So the 7 next to it over here, since that's 5 and above, right? If this number is 5 and above, you round that up to 6. So my answer here is going to be approximately 72.6. So I'm going to one more decimal place than the original data. That's our rounding rule. Okay, so let's try another example just to make sure we got this. So let's say these are the number of seconds on a time watch. So 1.82, 2.31, 3.57. Okay, so again, I'll use my X bar there to represent the mean of a sample. And I'm going to add all three of these. 1.82 plus 2.31 plus 3.57, all divided by 3. Okay, so 1.82 plus 2.31 plus 3.57, and that ends up being like 7.7 divided by 3. So now I'm going to divide that by 3. And you see I get this, again, I get this repeating decimal, right? This is like 2.566, and it goes on, right? And so I'm going to need to round this. So using the rounding rule, I'm going to go to one more decimal place than the data in my data set. And these are all to 2 decimal places. So I'm going to round the answer to 3 decimal places. Okay, so I need to round this 6 here. I'm going to round that up to 7 because of the 6 here. Okay, that's 5 or above. So I'm going to get 2.567 seconds. And that's going to be my average. Okay, so the idea here is kind of like when you're in a chemistry lab or a physics lab and the results can't be more accurate than the actual observations. So you got to know what the significant figures are in your observations, and then your results can't have any more significant figures than the ones in your observation. If you've done that before and it was confusing, don't worry about it, because we're not going to do that. This rounding rule, in a sense, takes care of that. It's one simple rule, and it just says we're going to round to one more decimal place than the observations in the data set. Okay, so I just have a couple more things to share here. And one thing is the notation for the mean. Okay, there's the population mean, and then there's a sample mean. And both of these are going to be important, especially later on in the book. So the symbol, excuse me, the symbol for the population mean looks like this. It's a lowercase m in the Greek alphabet, and it's pronounced mu. That's the actual name. Okay. To me, it looks like a cursive U, but it's mu. And the formula for the population mean would be the sum of x, so the sum of the values in population x, whatever that is, divided by the size of population x. And the symbol here that they use for the size of a population is capital N. That's the size of the population. Okay? So they're using a capital N to represent the size of a population and a little n to represent the size of a sample. Okay? So for the sample mean, we're going to use that x bar symbol. And again, you just say x bar, and that represents a sample mean. And the formula would be the sum of x, but this would be the sum of the values in sample x. And you would say you divide by little n, because little n is the size of a sample. So just a little bit of notational difference. Really, the calculation is the same, but if it's a population, you're using mu. If it's a sample, you're using x bar. And at this point, it's not so important, but when we get to chapters 6, 7, and 8, where we got both of these symbols going on at the same time, it'll be important for you to be able to keep the two straight, okay? Now, I want to share something about the shape of the data, and the relationship between x bar and the median, MD. Okay, so the mean and the median, the relationship between those two is related to the shape of the data. So the best way to see this is if your data set is symmetrical, like perfectly symmetrical, the same on both sides, then the mean and the median are going to be equal to one another. The mean is going to equal the median if it's perfectly symmetrical. One way to see this is the mean is actually the balance point of the data. It's where the data balances. And so if the data is the same on both sides, it's going to balance right there in the middle where it's split in half. Okay? And so one reason this is helpful is if you want to determine if your data set is perfectly symmetrical, all you have to do is calculate the mean and the median, and if they're the same, then it's perfectly symmetrical. Okay? But now, if you think of this thing here as kind of a piece of rubber that I can pull like this, and I can stretch that tail out, right? And that's going to be caused by having an outlier here on the right. So let's say you have an outlier on the right here. What's going to happen is the median is going to stay put. The median is not affected by outliers very much because it doesn't take into account how big the values are. Okay, it's just finding the middle value in the data set. So imagine like this is a clear piece of rubber, and as you stretch it out, the line for the median is just underneath the clear piece of rubber, but the line for the mean is like in the rubber, and it gets stretched toward the outlier. So the mean gets pulled towards that outlier while the median stays put. And so what you're going to get here is if your data set is right skewed, or your book would say positively skewed, then the mean is going to be greater than the median. Okay? They will these will actually be the way you use this usually is if you want to know if your data set is skewed, you calculate the mean and the median, and if the mean is bigger than the median, then you know it's going to be right skewed. Okay? Similar with the other direction here is if you have an outlier here on the left side, the mean or the median is going to stay put, but the mean is going to get pulled toward the outlier here. So if you have a left skewed data set, or as your book says, a negatively skewed data set, you're going to have that the mean is less than the median. So this is a way of telling whether or not a data set is skewed. Okay? You calculate the mean and the median, whichever one is bigger. If the mean is bigger than the median, it's right skewed. If it's less than median, it's left skewed. If they're the same, it's symmetrical. And what's nice about this is you can tell if it's skewed, even if it's only skewed a little bit. Okay, if it's only slightly skewed, these will be close to one another, but the mean will still be less than the median if it's slightly left skewed, or bigger than the median if it's slightly right skewed. Okay, so that's a nice thing to know. And then one other thing here. Let's say I have a qualitative data set. So let's say I have one down here, if I can find it. I'll just make, I'm not seeing, there it is. Here it is. So let's say I take a sample of people that have pets, and one has a dog, another one has a dog, one has a cat, someone else has a dog, someone has a fish, someone has a cat, another person has a cat, and a dog, and a bird. And let's say someone else has a dog, a cat, and a dog. And now we want to calculate a measure of center for this data set. Now, can I actually find the mean pet? And by that, I don't mean like, ruff, 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 ruff. I don't mean angry or mean. I mean the average pet. Well, if you think about it, that doesn't apply to qualitative data, right? Because there's no way to add these up and divide by the number of pets. So the mean doesn't apply. Well, what about the mode? Well, in this case, I can't put the data in order. So if you can't put it in order, there's no way to find the middle value. So the I'm sorry, I meant to say the median. What about the median? And the median's not going to apply, okay? So with nominal data that can't be put in order, there's no way to find the median. And then finally, the mode. In this case, I can find the mode. I just have to figure out which pet occurs the most. So there's 1, 2, 3, 4, 5, 6 dogs. 1, 2, 3, only 4 cats. And the fish and bird only occur once. So the mode is actually equal to the dog. And so in this case, if you have qualitative nominal data, the mode is the only measure of center that you can use. Now this leads to something a little interesting, because you could probably find some article out there that says something like the average pet in America is the dog. And so what do they mean when they say that? The average pet in America. Well, they don't mean that they've taken the average. They haven't calculated the mean or even the median. They must mean the mode. Okay, but they use the word average. And so you have this kind of this situation where people will use the word average to refer to the mean, median, or the mode. And you don't necessarily know which one they're using. Okay? And so this is a way that people can be misleading with statistics. It's by choosing which one best suits their needs, the mean, median, or mode, and reporting that one, but not telling which one you're reporting. So, for example, let's say you're wanting to impress an investor, and so you want the investor to think that the people in your neighborhood are rich. And so you might report the mean income, because the mean is usually bigger than the median. The incomes are right skewed, and the mean is bigger than the median. And that would be what you would do. But let's say you're wanting to get government support for your neighborhood, and the government's going to support a neighborhood that's poorer, that has more need. Well, in that case, you would submit the median income. You wouldn't give them the mean. Okay, you give them the median, because the mean incomes are right skewed, and the median is less than the mean, right? So you're going to choose the average that best suits your need, and that's known as the well-chosen average. And a lot of times, people will consider that one of the ways that you can be misleading with statistics.